Hello, my name is Erhan Budak. This is Manufacturing Research Laboratory in Sabancı University. Our research in this laboratory focuses on manufacturing processes and equipment, focusing on machining, particularly machining processes and machine tools. Machining is a very common process used in various industries such as machinery manufacturing, or aerospace, automotive, energy, and medical, etc. So this widespread use of machining processes is due to the ability of those processes to produce highly complex parts made out of various materials. Machining is a highly flexible process as the initial preparation is not very long, since dies and molds are not needed, making low volume production and customization possible and feasible. Furthermore, necessary changes along the production life cycle can easily and relatively quickly be adapted without major additional costs. As such, we have very close relations to the industry for improving machining process performance in applications. One important part of our research focuses on improving productivity of machining processes and machine tools through modeling and simulations. These involve development of digital twins based on mathematical models of these processes and machines, which enable simulations before the real process takes place. This is very important as digital twins mimic machining process in the computer environment using mathematical models of cutting process mechanics, dynamics, as well as machine tool behavior. This approach eliminates or significantly reduces the number of tests involving high number of costly trials and errors. Thus, it speeds up process planning, reducing cost of development, as optimal conditions can be obtained in digital environment before the real cutting action. Furthermore, potential problems which may happen during the process can be identified ahead of the time, and thus solutions can be found, eliminating damages to the part, tools, and the machine. This is an important part of digitalization in manufacturing operations towards increased performance and quality, as well as reduced cost of the development and the operation. Another important area of our research is on monitoring of machining processes towards detection of errors and faults. During real production, conditions of the machines, tools, processes, etc. may change due to various factors such as wear, material or tool quality, human errors, and so on. If these are not identified on time, they may cause problems, scraps, damages, and quality issues, reducing the yield of production, increasing the cost, and harm to the environment. This is also one of the main aims of Industry 4.0 activities, where the use of sensory information during operation is one of the main objectives. One of our present research projects is on development of a monitoring system based on simulations and machine learning techniques. Machine learning is in general based on real-time data, which may require long training time as some of the faults do not occur often. We use our process simulations to generate these faults in the digital environment to train the machine learning system and verify them, of course, with real machining tests. So far, very promising results have been obtained with high success rate in this approach. The outcome of this research will be an important step in unmanned production, making long-time dream of autonomous machining processes possible in one of the most important goals of our research. Machine tools and cutting tools, of course, play important roles in productivity and produce part quality in machining operations. Therefore, another important area of research activity in our group is on design optimization of machine tools and cutting tools. Again, digital twins are used to optimize them for improved performance. For optimization of machine tool structures, finite element methods and topographic optimization techniques are used to optimize the shape and mass distribution in a machine tool, reducing the moving mass as much as possible, for example, to increase the speed performance, or reducing the energy requirement during the motion of a machine. One important component of machine tools is the spindles. Their performance strongly affect the machining quality and the performance of the overall machine tool. So we have developed techniques in this area to model the spindle's thermal and mechanical behavior as well as dynamic performance to optimize their design. And so we use also mechanical and dynamic models to determine the optimal cutting tool geometries to obtain the best performance. Because the performance of machine tools are really key factors in machining operation performance. So we work closely with industrial partners in these areas to apply the outcome of our research in application. So the results of our research have been and continuing to be implemented in industrial applications in various sectors. In addition to the ones I mentioned, we have other research areas in our group and laboratory on, for example, abrasive processes such as grinding, with its various applications. Grinding in general is a process to improve the performance, the surface quality performance of the machine components. In some applications, though, it is also used as the main material removal process, especially in manufacturing of parts made out of difficult materials, such as the ones used in aerospace sector. We have been developing digital twins of these processes as well to predict process forces, generated heat, workpiece surface temperature, which are critical in these operations as they may cause surface integrity problems and other quality issues. We are also working towards improved grinding tools, such as the ones with texture surfaces, to improve the performance of these tools as well. These involve, again, use of digital twins for the processes. In summary, our research in this laboratory focuses on improvement of manufacturing processes through digital twins and sensor-assisted manufacturing methods. The application of reverse digital twins is another area that we are working on towards wider implementation of these methods in industrial applications. These developments involve, of course, intense process modeling and simulation, as well as application with various implementations. Our final goal in our research is to achieve unmanned manufacturing with improved performance through use of digital twins, intelligent monitoring systems, and improved machine and cutting tools.